So this is joint work with a current student at Cornell, Nirmal Shende, and a former student, Ujjal Altug. And it's about revisiting or taking a new look at feedback over just regular point-to-point communication channels and how much benefit it can give us and how to use it and how to get performance gains using feedback. All right, so if you were to go grab like a random information theorist off Fleet Street and say, how does feedback improve communication performance? Okay, so coding performance. I'm not really interested in complexity per se. Feedback certainly will give you kind of lower complexity schemes, but I'm looking at performance. So how does feedback give you improved performance? Okay, so this information theorist will probably give you the following list. So the first thing that comes to mind is memory, right? If the channel has memory, then you can use the feedback to kind of guess what's going to happen in the future and the noise realization and adapt your transmission accordingly. If the channel's unknown, then you can use the feedback to learn its distribution, right? And if it's unknown in like a Bayesian way, then this would actually be a special case of the first one, right? You can have like, variable versus fixed block length, right? So if the decoding time is not fixed, if you have like an average constraint, like on average you have to finish by time n, okay, then the encoder can use the feedback to sort of track the communication and end opportunistically early or late, so that on average you're done by time n, but you get a performance gain by kind of opportunistically determining the decoding time. That's like variable versus fixed block length. Similarly, if you have an average cost constraint where the average is not just over time, but also over the channel noise and the message and so on, then you can sort of opportunistically use more resource, more power, if you will, or less, depending on the channel realization, so like a Shockley-Kyleth type of idea, and you can do better there. Somewhat more subtly, so if the rate of the code is very low, then it's the minimum distance that matters. And feedback can effectively increase the minimum distance of the code. You sort of track the transmission, and then toward the end of the transmission, you look at the survivor messages. And if the rate is low, there are only a few of them. And so you map all those surviving messages to points that are very far apart in signaling space, and you get like this minimum distance boost from the feedback. All of this is point-to-point. If you have multiple encoders or decoders, okay, then feedback opens this whole new world of conferencing and collaboration and so on. And the question I'd like to understand is this it? Okay, so if I'm the information theorist you grab off of Fleet Street, I would give you this list. This is all the ways I know of. Perhaps someone knows of other methods that are out there. These are the ones I know of. I'd like to understand, are there others that we're missing, or is this it? Okay? And of course, the problem's not really well posed, right? 'Cause I can always change the model. Right? So maybe with a new model of communication, there's a way of using feedback that's not really captured by any of these things. You can never really rule that out. In particular, you can spend your entire life thinking about point-to-point communication and feedback and then never even realize that there's this whole other world here in networks. Okay, but I can make the problem well posed by saying if I consider a canonical model with a form that I assume away all of these things, okay, then can we either prove that feedback does not help, or can we uncover some new way of using feedback that's kind of been sitting under our nose this whole time? All right? That's what we're going to do. Is we're going to consider a canonical model where I assume away all of these known ways and see if we can either prove feedback does not help or find a new way of using it. Okay? So consider a model for which none of these apply. So here's the model. This is the most vanilla model, okay, that you can create. So it's just point-to-point communication over a DMC. Okay? You have k bits that you want to send over n uses of the channel. The channel is W, it's discrete, it's memoryless, it has a known distribution, point to point. There's no power constraint. A hard decoding time at time n, okay? So here's our measure of coding performance. So what rate can you sustain as a function of the block length n and the error probability epsilon? Okay, how many bits can you send as a function of the block length and the error probability? I can consider this quantity both without feedback and with feedback, and we'll consider the simplest form of feedback there is, just straight, full output feedback. All right. So these are the two quantities of interest, and we're going to consider them in the, in the high rate regime. So the capacity theorem, both with and without feedback, says that these two quantities converge to the capacity for any epsilon as n goes to infinity. In both cases, at least for for interesting channels, interesting DMCs, the rate, the speed of approach is 1 over square root of n. Okay, so we can consider the constant in the 1 over square root of n backoff. We'll call it the second order coding rate. So this is defined both with and without feedback. All right, and the question is, can I expose a difference between these two quantities, and how? And what is the mechanism? Okay, so to first order feedback does not help. Okay, to second order, does it help? And if so, how? Okay, and I'm considering rates very close to capacity, so it's a high rate regime, so that minimum distance thing doesn't crop up. Okay, so we've assumed away like all the known ways in which feedback can help, right? It's point to point, it's a known channel, it's a memoryless channel, it's high rate, fixed block length, there's no cost constraint. Like all the standard ways, all the classical ways of using feedback are not accessible here. Okay, so can we either prove these two things are the same, or can we find a new way of using feedback? Okay, so without feedback, the second order coding rate is known. So I say for any DMC, but throughout the talk, I'm assuming these constants are positive, so there's a slight caveat there. But anyway, so for any DMC, let's say, there's a result from Strauss in 1962. Okay, that gives you the second order coding rate. This phi function is the standard normal CDF, inverse CDF. And Vmin and Vmax are channel constants that are defined later. So this is what we'd like to beat. And first, a note of pessimism. Okay, for some DMCs, you can show that feedback does not improve the second order coding rate. In particular, if the channel is symmetric, okay, then the second order coding rate with and without feedback is the same. Okay, so certainly we can't for all DMCs expect to see an improvement here, but perhaps for some. Okay, and the main point of the talk is that an improvement in the second order coding rate is possible for some channels using what I consider to be a novel mechanism of using feedback. Okay, so I can describe the idea simply using coin flips. Okay, so suppose you have two coins, you have one in each hand, and you're going to flip them. Okay, and if you flip the one in your left hand, you get $1 if it comes up heads, and you lose $1 if it comes up tails. The right hand coin, you get $2 if it comes up heads, and you lose $2 if it comes up tails. Both coins are fair, and you know they're fair. Okay, so equivalently, you can say you have one fair coin, and you decide whether to wager $1 or $2. Okay, same thing. There are going to be n flips. Okay, and you start with a certain amount of money, which could be positive or negative, depending on alpha here. And the objective is to minimize the chance that your wealth at time n is negative. Okay, and the question is, what are the good strategies, and does feedback help? And feedback here would mean the following. I could a priori just declare which coin I'm going to flip for each of the n time steps, okay? Or I could sort of track my wealth over time and then adjust which coin I'm flipping depending on how I'm doing. Okay, so that's the question. When I say feedback, does feedback help? That's what I'm referring to. All right, so feedback does help, and if you think about this for a while, you come up with the following natural strategy. So here's a typical realization of this process. You start with a certain amount of money, and then you sort of control the size of the step in this random walk. And remember, your steps are always zero mean, right? You're always either moving up 1, plus 1, minus 1, or up plus 2, minus 2. Okay, so your step forward is always zero mean, and you're only controlling the spread. That's the only thing you can actuate here. Okay, you start with a certain amount of money. Your goal is to minimize the chance that you end up negative at time n. So minimize the probability I end up in the shaded region. I start wherever I start, and I know where I start. Okay. So you're taking these steps. So what's a good strategy? So suppose you're here, right? So you have a positive amount of wealth. At this point, you're expecting to win, right? You're expecting to end up over there, right? So if you're expecting to win, you want to minimize the variance as much as possible to concentrate the distribution around that mean, which is favorable, right? So you'd flip the plus 1, minus 1 coin in that case, right? And I'll call that plain timid, okay? On the other hand, suppose you're here. Suppose you've dipped below 0, okay? At this point, you're expecting to lose, right? Because your expected wealth at time n is going to be there. So if you're expecting to lose, you want to actually increase the spread of distribution as much as possible to throw as much probability up above 0. So this is not very intense. Throw as much probability up above 0 as you can, right? So in that case, you want to play bold, right? So use the plus 2, minus 2 coin down here. It's a reasonable strategy. You can prove it's optimal in the continuous time limit as n goes to infinity. So let B be a standard Brownian motion, and let alpha be a constant, which is your starting point. And you consider this controlled diffusion. So you start at alpha, And then at each time, you get to instantaneously control the variance of this Brownian motion as it evolves over a range. And your goal is to minimize the chance the Brownian motion ends up below 0. And you might start above 0, or you might start below 0. So the problem's meaningful either way. Okay, alpha is just some constant. All right, so there's this really cool paper by McNamara in 1983 where he shows that this bang-bang controller that just does minimum variance whenever your wealth is positive and maximum variance whenever it's negative is optimal among all choices of sigma. So you never use the intermediate variances. You're just always going maximally timid or maximally bold, depending on whether you're expecting to win or whether you're expecting to lose. OK, so that's the theory. So here's the reference to hockey. Okay, so you can find examples in the real world of people or animals, using this strategy. So in hockey, there's this notion of pulling the goalie. Okay, so if you're down by, I'm not a hockey expert, but I found this on the web. Okay, so if you're behind by several goals late in the game, okay, then it's advantageous to pull your goalie, replace the goalie with another offensive player, and now you're sort of have an extra offensive player, and you're more likely to score a goal. Of course, it's risky because your goal is completely unguarded, but you're expecting to lose, right? So you want to get fat tails here, and that's a way of getting a fat tail. All right, so that's in hockey. McNamara himself, in his '83 paper, points to papers in the zoology literature on foraging animals, and they've observed that animals that are near starvation engage in riskier foraging strategies than animals that are not near starvation. Okay, so you can find various examples of this. There's this quote in Cornell Thomas I think is very apt. If luck is required to win, we might as well assume we'll be lucky and play accordingly. I read that as a PhD student when I first took information theory. Somehow it didn't really sink in. I read it, okay, yeah, it makes sense. Okay, but now I really get it, right? I understand what's going on. If I may make a personal statement, like working on this project has actually changed the way I make decisions in my everyday life, okay? In the sense that play timid when you're expecting to win and play bold when you're expecting to lose. I found just be a useful mantra, in general, okay? There's a certain model here, right? I mean, if you end up below 0, you lose no matter how close you are. If you're above 0, you win no matter how close you are. So the model's kind of sensitive to that, but there are situations in life that are like that. Hockey games, NSF proposals, various things of that sort. Okay, so we're going to map this to communication channels. This requires some notation, unfortunately. All right, so let Q star be the capacity-achieving output distribution. So channels can have multiple capacity-achieving input distributions, but the output distribution they induce is all the same. I'll call that Q star. All right, so here are the Vmin and Vmax quantities that we introduced earlier. So mutual information, or capacity, is basically expectation of this likelihood ratio. We want to consider the variance of that likelihood ratio, maximized and minimized over the input distribution. Okay, so consider all the capacity-achieving input distributions and find the one that minimizes and maximizes the variance of that likelihood ratio. Okay, so it's called Vmin and Vmax. So that's already in Strassen's paper. Let Pmin be the minimizer, Pmax the maximizer. All right, and then we also need a couple of other quantities which are similar. So consider the minimum and maximum maximized and minimized over the inputs x, okay, rather than over the input distribution. Okay, so Vmin and Vmax are sort of like averages of these kinds of quantities over the x, and then this is like the pointwise minimum and maximum of the variance. So you can order them like this. All right, and throughout the talk, we'll assume that all these variances are positive. All right, and then last bit of terminology. So we'll call it channel compound dispersion if these variances are different, and simple dispersion if they're the same. Compound dispersion channels exist. So here's one that we cooked up. It's not necessarily like the smallest dimensional example you can create, but it's one that's easy to work out the details for. So it's basically two 3x3 symmetric channels just pasted together to create a 6-input, 3-output channel. And what you do is the following. So fix P to be something, and then you choose Q here so that the row entropies are all the same. Okay? And then the capacity, there'll be a whole segment of capacity-achieving input distribution. So a distribution that puts mass 1/3, 1/3, 1/3 on the top 3 rows and 0 on the bottom 3 will be capacity-achieving. Likewise, you can put mass 1/3, 1/3, 1/3 on the bottom 3 and leave the top alone. That's also capacity-achieving. If you use the bottom one, you get a low variance. If you use the top one, you get a larger variance. Okay, so these things do exist. All right, so here's the idea. So at a very high level, okay, we're just going to apply the McNamara intuition. So we'll sort of use a timid communication scheme or a timid signaling scheme when we're expecting the communication to be successful, and we'll switch to a bold one when we're expecting an error. Okay, so here's the idea in its kind of simplest form. So suppose we have feedback. Suppose the channel is compound dispersion. And suppose, just for the sake of simplicity for now, that we only use the feedback once at halfway through the block. Okay, so we sort of transmit, we use like a non-feedback code for the first half of the block. At time n/2, we use the feedback to decide what to do then for the second half of the block. Second half of the block is then non-feedback except for that one initial choice. Okay, so we use a code with like 3 subcode books. Okay, so each has time duration n/2, that's half the block. For the first half of the block, we always use this code book. Okay, and the code words are generated IAD Pmin. This is assuming we're approaching capacity from below. Otherwise, you do Pmax here. But anyway, so the first half of the block has this fixed code book that you always use. So if you want to send message 2, you just send that code word, and that's that. For the second half of the code book, we have 2 possible, for the second half of the transmission, we have 2 possible code books to use. So they're both duration n/2. And one is IAD Pmin, and one is IAD Pmax. And this top one is like the timid signaling scheme, and the bottom one is like the bold signaling scheme. Okay, and what we do is, if you want to send message 2, you send this code word. Okay, and then time n/2, you see how you're doing. Okay, so this is the test we used. So you look at like roughly the empirical information conveyance over the channel during the first n/2 time steps, and you compare that against where it should be. And if you're ahead of schedule or on schedule, okay, then you continue using your timid scheme. But if you're behind schedule, like the information conveyance is too low, given the realization of the channel, okay, then you switch and do the bold scheme from there on out. So we call this timid bold coding, right? And you can show that even this simple form that only kind of makes a switch once at halfway through the block will give you a second order coding rate improvement for any compound dispersion channel. But of course, you can do better, right? I mean, it makes sense to just adjust your strategy after each time step, not just once. So this gets technically more involved. I can give you this statement. Okay, so we define this function here. It's a little bit busy. It's a function of 3 parameters. There's the error probability, and then like 2 standard deviation quantities. Okay, and basically think of this as the following. So gamma is like the highest starting point you could have in McNamara's continuous time controller, so that if it can adjust the variance between S1 squared and S2 squared, then the probability that it ends up below 0 is less than epsilon. Okay, so it's like the highest starting point you can have in McNamara's problem, or I guess, sorry, the lowest starting point. Yeah, sorry, the lowest one. Okay, so the theorem is for any DMC with feedback, the second order coding rate with feedback is lower bounded by this gamma function evaluated at Vmin and Vmax. So the corollary, feedback improves the second order coding rate for any compound dispersion DMC, because you can prove this, as long as Vmin and Vmax are different, this gamma function is strictly bigger than what was in Strawson's result. So we're getting a second order coding rate improvement. If the channel is simple dispersion, then Vmin and Vmax are the same. This gamma function collapses back down to what Strawson had. Okay, so we can show at least for some channels, we can get a second order coding rate improvement with feedback. But we also know for some you can't, right? So we know if the channel is symmetric, then feedback does not give you a second order coding rate improvement. So we know there are some channels for which it does, some channels for which it doesn't. That raises the question of, like, can we delineate the two? So for a given channel, can I determine whether feedback gives me a second order coding rate improvement or not? Okay, so the good news is we can answer that question. The bad news is the set of channels for which you get the gain is the smallest possible. It's just compound dispersion. Okay, so we can prove the second order coding rate is improved with feedback if and only if the channel's compound dispersion. Okay. this raises, so a third question that comes up then is how much does feedback help? Okay, so for simple dispersion channels, feedback does not help at all at the second order coding rate. For compound dispersion channels, you get a positive gain, and we have a lower bound on that gain. That was the previous theorem. But can we upper bound the gain, right? So, or can we prove that timid bold is optimal for those channels? So we have a theorem on this, and this is like the one incomplete result in this work. So here's the gamma function rewritten. Here's the achievable result, okay? And so we can prove the following converse result, the following impossibility result. So it's stated for any DMC with feedback, but it's really only interesting for compound dispersion channels, right? For simple dispersion, we already know the second order coding rate with feedback. So for compound dispersion channels, we don't, but we can prove the following upper bound. It looks very similar to the lower bound, especially when I choose my notation in this sort of suggestive way. So the difference between the two is the following. So remember, gamma is like the lowest starting point in McNamara's controller, where you can ensure that the chance you end up below 0 is less than epsilon, right? And as a function of the variance parameters that it gets to vary between. So in the lower bound, you allow the controller to vary between Vmin and Vmax. And then in the upper bound, you allow it to vary between nmin and nmax, which is like a wider window. Okay, so that's the gap between the two. And for this example, it turns out that Vmin is actually equal to nmin, and Vmax is nmax. Okay, it's because we have like 3 rows with the highest possible variance and 3 rows with the minimum possible variance. And our Pmin, puts all of its mass on those bottom rows, and our Pmax puts all the mass on the top rows. So you get the same minimum whether you minimize over input symbols or over input distributions. So for this particular channel, the upper and lower bound coincide. That doesn't happen in general, of course, but for this particular channel, it does. And so you can plot the second order coding rate without feedback and with, and you can see you get a gap for all epsilon. All right. So how much time? 3 minutes? All right, so all the proofs are in this talk, but I think with 3 minutes, it's probably not even worth trying. So let me just flip through all of this. I think I'll just mention the most interesting part of the proofs is that at one point we use a different result of Strawson from the 60s on martingale embeddings. So he shows that if Sn is a square integrable martingale starting at 0, okay, then you can couple this martingale to a Brownian motion with stopping times, okay, so that your martingale equals the Brownian motion stopped at those stopping times. And moreover, the expected duration between the stopping times is given by the incremental variance of your martingale. It's like the variance of the martingale difference sequence, okay? And we use this because we can, using standard methods, we can sort of reduce the feedback coding problem to a discrete time version of McNamara's problem, okay? But we then want to assert that the bang-bang controller is optimal. We don't know it's optimal in discrete time, only in continuous time. There are standard methods of taking like discrete time, processes and showing they converge to continuous time limits, but those results all assume that your discrete time process is very nice and controlled, and we're proving an impossibility result here. The code could do really wild stuff, and so we can't just easily switch from discrete time to continuous time. But with a result like this, we can actually take our discrete time controller and then view it as choosing stopping times in a Brownian motion, and then thereby actually view it as a continuous time version of the controller directly, and then apply McNamara's result. So anyway, using Brownian motion scaling properties and so on, and that's that. All right, so I think the most important takeaway from the work is really this qualitative notion that there's another way of using feedback in even point-to-point channels. So again, there are classical ways of using feedback. You predict the noise realization using memory. You learn the channel law. You randomize the decoding time, randomize the transmission power opportunistically, increase the effective minimum distance using feedback. All of these have been known since the 60s, 70s. And now to that list, we can add one more small one, which is use timid bold coding. All right, thank you.